Hey everyone, welcome to VishElectronics. Today we are going to start with linear integrated circuits, and particularly we are going to be looking at integrated circuit fabrication. So we're going to be looking at the introduction and some classifications of integrated circuits, and also the complexity and the types of integrated circuits which has been developed till now. So in the topic fabrication, let's look at the word fabrication. Fabrication is manufacturing something. The meaning of fabrication is manufacturing something. So in our daily life, we can say, textile fabrication, automobile type fabrication, and so on and so forth. Fabrication is manufacturing something. So we are living in a period of microelectronic revolution, which means that any electronic device you take, any electronic device which is you take around you, they have these electronic components, they have these microelectronic components within them. And the best example for microelectronic components are nothing but transistors. We as electronics engineers know how important electronics are and where and all the electronics are used. And electronics, some of the applications of where these electronics are used are business transactions such as to display information, digital display, and it is used in aerospace for communications, tracking the satellite, etc., GPS, etc., mobile phones obviously, and digital computers, control, and so on and so forth. So let's move to the other side, the integrated circuit. So integrated circuit is nothing but an electronic circuit, but they are the fundamental building blocks behind the functioning of all electronic devices which you see, practical electronic devices which you see. So a simple diagram for an integrated circuit looks something like this. So this is a very primitive integrated circuit. So these are the different pins. So these are the different pins in the integrated circuit. So this is a very primitive integrated circuit, and so basically there are some properties associated with this integrated circuit. And some of the properties of these integrated circuits include that they have components which are very small. It is a miniature meaning small electronic circuit, and they are low cost, which is a really important feature when we actually come into the industry point of view. They are low cost electronic circuit, and they contain billions of transistors, capacitors, resistors, and so on and so forth. They have a lot of components within them which are mounted or which are joined irreparably together on a single silicon chip, which basically is irreparably together means they cannot be taken away that easily. So they are joined irreparably on a single silicon chip. For the reason why we use silicon is because of certain advantages of silicon over the other semiconductor material, which is germanium. So we use silicon chip more often than germanium. And one other important point, when we look at these transistors, capacitors, and resistors, you may ask, in our daily life, the transistors are, it is, we can hold those transistors and stuff like that. But in the ICs, they are really small, which automatically makes them that these transistors, resistors and capacitors are not similar to what we see in our daily life, discrete components which we hold, which we perform our experience with. They are not similar in appearance, though they perform the same electrical functions. Not they, so they are not same in appearance, but they have similar electrical functions. Which means, a transistor should switch the signals, means it will do it. That even a discrete one will also do. But they are not similar in appearance. A resistor will offer resistance. So that this IC resistor will also do the same thing. The normal discrete component resistor will also do the same thing. But the physical appearance is different. So these are some of the properties of ICs, very important properties of ICs. So basically in this chapter, we are going to be looking at certain fabrication processes which are used in manufacturing these ICs. So the question is, there are billions of transistors, capacitors and resistors. How did they put all these billions of transistors inside the IC? So what is the process? What is the process of manufacturing an IC? So this is the basic questions. So both metal oxide semiconductor transistors, MOS transistors, and also bipolar transistors, and how are introduced in this chapter. How an MOS transistor is created and how a bipolar transistor is fabricated, and so on. So this is what is the basic outline of what we are going to study in this chapter. So another, if you are a curious man, you might ask, if there is discrete components if we have the discrete components, then why do we need to create an IC? Is there any advantages of ICs over what we see in our daily life, discrete components? So some of the advantages of ICs over normal discrete components include, obviously, as I told, miniaturization. So the miniaturization leads to increased component density. So now what is this increased component density? So we reduce the size of the transistors, resistors and capacitor components used. We reduce the size of the components used in IC by certain processes such as photolithography, advanced lithography, FinFET technology, and so on. So we use these processes to reduce the size of components, and these components are fitted onto the ICs. So basically we want to increase the number of transistors, the transistor density within the integrated circuit. So this will lead to more efficient control flow of the current flow, the control of the current flow within the circuit. And we also have to develop circuits which consume less power and also higher operating speeds, and so on and so forth, improved performance, energy efficiency. So these are the reasons why we reduce the size of the components inside the ICs. And photolithography, so let's talk about photolithography. So in photolithography there is light. I'll take a different color. So there is light, and the light is made to fall on a silicon wafer. Imagine, let's say this is the silicon wafer, and this silicon wafer is coated with a coating of photoresist. So this silicon wafer is coated with a chemically coated, light sensitive chemically coated photoresist, and on this a photo mask is placed. So a photo mask is something like, imagine this is the photo mask, and this is the impression that we want to create on the silicon wafer. So this is a photo mask. So light is made to fall on these photo mask. So when light falls on this mask, the photoresist material absorbs the light and certain impression is created on the silicon wafer due to this photo mask. So basically it is the process in which light is allowed to fall on the photo mask, which has the certain desired pattern which we want to impart on the silicon wafer. On the semiconductor silicon wafer, and so once we get that impression, these are the unrequired parts. We don't require these parts, right? Because it is not even required, it's not of any use. So by a process called etching, chemical etching, we remove those unwanted or undesirable parts. So this is the basic process of photolithography, simply speaking. So looking at another type of technology which is used to reduce the size of the components used in ICs include advanced lithography techniques such as extreme ultraviolet lithography. So what is this extreme ultraviolet lithography? What does this mean? So basically we use very short wavelengths of light to design intricate patterns on the substrate, which means in our visible spectrum of light, we have a spectrum like this, right? So in our visible spectrum we have let me draw a box. Not a very big box. Okay, so this is so let's say this is gamma rays and this is X-rays, and this is the UV which we are going to be talking about, and this is the visible spectrum, the different colors, and beyond this is the IR, infrared waves, and then comes microwave, and then comes FM radio waves and AM radio waves, and then comes long radio waves. So this is the visible spectrum lies here, all whatever we see. So I'm not going to draw it in very specific. This is the visible spectrum, and as you can see, this is the UV area which we are interested in. So in the visible, in the spectrum, as we go like this, the frequency increases, and as we go like this, wavelength increases. So which means this has short wavelengths. UV has shorter wavelengths than visible spectrum lights used. So that is why we use ultraviolet rays, which has very short wavelengths, to design intricate patterns on the ICs, on the substrate. So this is one type of advanced lithography technique. Another technique include electron beam lithography, which means we use a very high intense beam of electrons to design the intricate pattern on the substrate, on the silicon wafer. We focus a high intense beam of electrons onto the photomask, thereby creating an impression on the substrate. And we also some other examples of uses. So basically this uses electron beam. And another example for advanced lithography techniques include nano-optical technology. So what is nano-optical technology? So light is taken and we are going to use nano elements, and we are only going to make the light pass through this element. The light can be big, but only the light which is passing through this narrow element is focused onto the silicon wafer, thereby creating a smaller version. Though the light emission is wide, we are focusing it within a small nano element, thereby reducing the light into a specific nano beam, and we are making it to fall on the photomask, which has the desired pattern, and thus we are creating an impression. We are getting a very small impression. So basically we perform this miniaturization to reduce the size of the components inside the ICs, and this leads to the increased component density. And if we increase the component density, we will have more efficient control over the current flow and other stuff like that. So this is why we want to increase the component density within the IC. So another technology is FinFET technology. FinFET technology is a little bit advanced, in which we are going to use a 3D transistor design. So what we will be studying is mostly 2D technology transistors, but this is a 3D transistor design, which enables better control of current flow. So in comparison with 2D transistor, this has better current flow control. So this also enables the creation of smaller transistors. So smaller components, greater component density and greater use. So enables creation of smaller transistors. So FinFET technology will be dealt in the following lectures. And another very significant process we use is 3D integration. So basically these are all different techniques: photolithography, advanced lithography, FinFET technology, 3D integration. These are all done to miniaturize, to enhance the component density within the ICs. So 3D integration is stacking multiple ICs. We have one IC, right, and it has some pattern, let's say, and we are stacking another IC which, let's say, has something like this, and we are merging it on above one another, such that the resultant will be something like this. So we are stacking one above the other, we are stacking one IC layer one above the other, and thus we are enhancing the component density, and we are reducing the unwanted space, which means this space got occupied by this, so thus we have a full, that space got covered. So this is what we mean by 3D integration. So stacking of multiple layers of ICs one above the other, and the space in ICs are more efficiently used. So that is for miniaturization. So another advantage, very awesome advantage of why we use ICs over discrete components are cost reduction, and this is due to batch processing. So batch processing is nothing but manufacturing lot of ICs on the single silicon wafer. This leads to low cost per product, and efficiency and time reduction. So these are the advantages of why we perform batch processing. So there is a single silicon wafer, a big silicon wafer, and we are performing lot of ICs. We are processing lot of ICs on the single silicon wafer. So this will reduce the cost per product of each ICs, and it will also reduce the time, because and all these ICs will have the same properties as the other. So if we want to create ICs in bulk, if we want to create ICs in industries, then this batch processing techniques are used. And the other advantages of why we use ICs over integrated circuits over discrete components include elimination of solder joints, which leads to increased system reliability. So what is the meaning of this? So soldering is a mechanical process of connecting the wires and components together. So due to mechanical stress or due to the temperature differences and a lot of these external factors, environmental factors, the soldering which connects the wires and the components together, it can degrade, it can get weakened over time, and this will cause the malfunctioning of the ICs. But by eliminating these solder joints, these mechanical failures, the malfunctioning of ICs due to mechanical failures can be reduced. So solder joints can offer electrical resistance. So in mechanical stress, due to the connections of wires and the components by the process of soldering, there can be some resistance within the soldering, and this will cause the reduction of the current within which may be flowing within the wires and the components. But if we eliminate these solder joints, then there will be the current is going to be maximized, and it will uh, give the maximum current flow into the ICs. So this is why we use ICs. In ICs there is elimination of solder joints, while in our discrete components we solder it, and there may be electrical resistance, and there may be mechanical stress, and so on and so forth. So these are the some of the uses of why we are eliminating the solder joints in ICs. So another important, so why we do this is to reduce mechanical failures and reduce electrical resistance at the solder joints. Right. So coming into the next advantage of why ICs are preferred over discrete components are functional improved or increased functionality. Very complex circuits can be mounted on this IC, which leads to which means that the ICs can perform different tasks. Complex circuits include a very large number of components, and so all these components, increased component size density, if we are able to integrate all of this onto that single chip, then that silicon chip, that IC would be capable of performing a lot of different tasks, and hence more sophisticated processes, more sophisticated analysis, and hence this increases the functionality. It can perform a variety of different tasks. And another important is, so improved functionality is complex circuits causes ICs to perform different variety of tasks. If in our discrete world we will be able to only create this kind of circuit only up to some certain complexity, but in ICs, since the components are reduced, we can create a very complex circuit in which the ICs can perform a lot of different tasks. So another advantages of ICs include power consumption reduction. So how is power consumption reduced in ICs? So power consumption in an electronic circuit is directly proportional to square of the voltage. So that's why even a small reduction in the supply voltage can reduce the power significantly. For smaller transistors, we have to give smaller supply voltages, and that is done in, so smaller transistors require smaller supply voltage, and hence the power is drastically reduced, because as we see in this relation, it is directly proportional to square of the voltage. And this is where FinFET technology comes, because in FinFET technology we saw that smaller transistors are created in FinFET technology. So, and this is this is by reducing the voltage supply. Manufacturers also employ design techniques within the IC itself such that it will only consume very low power, such as there is clock gating. So this is 1, this is 2. So in clock gating, data gating, power gating, and so on. I will come back to this later in the following videos. And these are design techniques which manufacturers use for low power consumption. So they specifically design the integrated circuit with these in order to reduce the power consumption in the ICs. So the next important advantage is matched devices. So what are matched devices? So all the ICs are manufactured, lot of ICs are manufactured on a single wafer, and hence all of them have the similar electrical functions. There won't be any disparity. If you manufacture them individually, there may be a little disparity between the electrical functions, but since you are preparing a lot of them on the same wafer, they will have the same electric functions. So this is the advantage of ICs, matched devices. And increased operating speeds due to parasitic effect reduction, which means that parasitic effect is nothing but so let me write it: increased operating speeds due to reduction of parasitic effect. So parasitic effect basically causes signal interference, and it will cause the signal delays which are with the signals which are passed in ICs. It can introduce signal delays within the ICs. So if we reduce this parasitic effect, the signal can be more prominent and it can propagate quickly without any delay, which allows the circuit for fast operation. So this is what we want. We want the ICs to perform very quickly. We want it to perform at a very high speed. So we have to reduce the parasitic effect. So there are different types of parasitic effect. Parasitic effect can include parasitic capacitance, resistance, parasitic resistance, inductance, and so on. Inductance, and so on and so forth. Parasitic capacitance is nothing but there is a capacitance which exists between the conductive elements in an IC, which means such as like a metal connection joint and semiconductor substrate layers, etc. And the parasitic capacitance stores and releases this electric energy, which causes, since it stores for some time and then it releases, it causes delay in the signal propagation. Especially it affects the high frequency circuits. So this can lead to signal interference and signal delay, and it can also increase the power consumption. So it stores electrical energy for some time, and this will cause the signal delay. And resistance. So parasitic resistance between the metal joints and the semiconductor layers can exist. So this parasitic resistance causes undesirable voltage drops and power dissipation, affecting the overall efficiency of the circuit. The output is affected. So so undesirable voltage drops. So these are the some of the parasitic effects which we see in ICs. So these are the advantages of integrated circuits over normal discrete components which we see in our daily life. Now we will look at the classification of integrated circuits. So in ICs, the most common ICs we use in our daily life are digital ICs and linear or analog ICs. And what are these linear ICs and digital ICs? So the linear ICs, they are also called as analog ICs, while the digital ICs, they are also called as non-linear ICs. Okay, so in digital ICs, the input can only be 0 or 1. The output can also be 0 or 1. Input and output can only take the values 0 and 1. While in linear ICs, continuous range of values can be taken for both input and output. These digital ICs are used in microprocessors, memory elements, and so on. While the linear ICs are used in amplifier circuits such as audio amplifier circuits and radio amplifier circuits and so on. So operational amplifiers, which we'll be seeing, which is a very important concept, we'll be seeing in the following lectures, and voltage regulators are also coming under linear ICs. So op amps and voltage regulators come under LIC. So we are interested in LIC, we are not interested in digital ICs as of now. We will be looking only at linear ICs from now onwards. So in linear ICs, there are less number of transistors than in digital ICs. Why? Because in digital ICs, we have to perform, so let me write it, less number of transistors in LIC than DIC. Why? Because the nature of the functions which we use in digital ICs include such as arithmetic, logical, and these kind of functions. They require complex digital signal processing and computation. So these functions require a lot of transistors because they have to create logic gates, they have to perform memory elements. So microprocessor contains a lot of memory cells, and all these memory cells require large number of transistors. So extensive memory capacity and these extensive complex logic functions increases the number of transistors within DIC. So complex functions and memory why in DIC. So this is the reason. So in digital ICs, the design is not as complicated as that of LIC, but design is very complicated in LIC. Why? It's because why? It's because um, analog circuits or the linear integrated circuits are affected by a lot of external properties such as noise, temperature, and variations in environment factors, so on and so forth. So in order to counter all these environment factors, we need to make the design of LICs really complicated so as to attain full functionality. So the design is very complicated in linear integrated circuits. So basically, in order to develop this, we will be looking only at linear integrated circuits from now on. We won't be bothering about digital integrated circuits. So in order to create this linear integrated circuits, two types of technology were developed. For manufacturing LIC. So one was monolithic technology, the other was hybrid technology. So in monolithic technology, the ICs created by using monolithic technology were monolithic ICs. They were called monolithic ICs, and obviously hybrid ICs. So the ICs which were created using hybrid technology are called hybrid ICs. So in monolithic ICs, so let's talk about monolithic ICs. In monolithic ICs, the active components, the passive components, and the interconnections between the different components are done on the same silicon chip. That means we have the same one single silicon chip, and we add the active components such as transistors, we add the passive components such as resistors, and we interconnect these different components on the same single silicon chip. So basically monolithic ICs are uh, are uh, are manufactured in industries where we require large number of identical ICs. So if we want large number of identical integrated circuits, we create monolithic ICs because it is done on a single silicon chip. And so this is what is monolithic ICs, which is done on single silicon chip. All the active components and the passive components are interconnected together on the single silicon chip. In hybrid ICs though, all these active components, passive components, and their interconnections are done on a ceramic substrate. Okay. The different components, the different components are attached to a ceramic substrate. So in monolithic we used silicon, but in hybrid ICs we use a ceramic substrate instead, and all the components are attached to the ceramic substrate, and the interconnections between the components are done. All components are attached. Components include active devices and passive devices. So these components are interconnected by metal bonds. Okay, so they have a specialized pattern of metallization patterns and wire bonds. So these are not connected with the substrate, so they have special metal wires and special metal pattern wires and wire bonds, and the components are interconnected with each other. So since we use specialized metallization pattern, you can guess that they can only be manufactured in small quantities. Yeah. So coming into the broad overview of integrated circuits, so we will look at the classification. So there is integrated circuits, and they are divided into monolithic integrated circuits and hybrid integrated circuits. So monolithic integrated circuits are further divided into bipolar and unipolar, which means that how did they classify monolithic into monolithic into bipolar and unipolar? Based on what active device we are using in the monolithic IC, whether it is a BJT, for example, or whether it is a FET. So if we use BJT, then it is called bipolar monolithic ICs. If we use FET as the active device, then it is called unipolar ICs. So in unipolar ICs, they are further classified into MOSFET and JFET, metal oxide semiconductor field effect transistor or junction field effect transistor. Though, and the bipolar ICs, they are classified, so unipolar ICs are classified based on what FET they are using, what type of FET used, while the bipolar ICs are classified into two types based on isolation type. Now what is isolation type? So isolation is done to prevent the electrical interaction between the different transistors in a circuit. One transistor and the other transistor should not touch with each other, and because if they touch, then it will cause the leakage currents to flow, and it will also cause the interference of signals, and it will lead to delays and so on and so forth. So we should isolate the different transistors from them. So this is why isolation is used. So there are two types of isolation techniques in bipolar bipolar ICs. They are PN junction isolation and the other is dielectric isolation. So in dielectric isolation, we have an transistor, let's say, and in that transistor we are covering it with a layer of silicon dioxide, which is an insulating layer. And why we are doing this is because we want to fabricate, we want to insulate the transistor from the other transistor, so that this isolation is achieved and we can avoid the interference of signals and so on. So we are coating silicon dioxide on a transistor, and this will insulate the transistor from other transistor. So this is dielectric transferring, the dielectric isolation. In PN junction isolation, we use PNP transistors or NPN transistors and so on. So by applying appropriate reverse bias to PNP transistors and by employing reverse bias to NPN transistors, we create a depletion layer according to the reverse bias we applied, and this will stop the current flow in one particular area, and the current flow will occur in one particular direction. So if we apply reverse bias to PNP transistors, the the collector base junction, there is a depletion layer formed in the collector base junction, and this will cause the electrons cannot flow from the collector to the substrate. While in NPN transistor, there is a depletion layer which is formed between the base and the substrate. So there won't be any electrons which flow from the emitter to the substrate. So these are the different types of isolation techniques used in bipolar ICs, and this is the broad classification of the ICs used in our daily life. So I hope that this lecture was useful to you guys, and I'll see you guys in the next video. Thank you.